Okay, so question 3. By expressing cos 2x in terms of cos x, find the exact value of that expression there. It is interesting, isn't it, that you know, we sometimes think of the modules as being separate, core 1, 2, 3, and 4, but they're really not, are they? And everything links in together. And so we're in core 4, and core 3 was all about trig identities, but we start off by having to do a kind of classic core 3 trig identity thing. You may have remembered this, you may have learnt it, or you can go from the formula booklet where it says cos A plus B is cos A cos B minus sin A sin B. So cos 2x must be cos squared x minus sin squared x. That's not quite done what they said. They said express it in terms of cos x. So we remember that sin squared is equal to 1 minus cos squared x minus 1 minus cos squared x. And if we collect things together, 2 cos squared x minus 1. So there, oh, I missed out an x. So cos 2x is 2 cos squared x minus 1. That's the first bit done, expressing cos 2x in terms of cos x. Find the exact value of this expression here. The other thing that we must remember, and we haven't mentioned that, but we talked a little bit earlier about differentiating sine, cos and tan, and here we're integrating some trig functions. It's vital, isn't it, that we have to be working in radians as soon as we start doing any calculus with all of this stuff. We know this, don't we? But as soon as there's any differentiation or integration involved, we must be completely in radians and not kind of think about degrees at all. It's all right in vectors, because we're not doing any calculus, but once we get into anything else in core 3 or core 4, we need to be working in radians if there's calculus involved. Right, so this is what we're integrating. The integral from pi by 4 to pi by 3 of cos 2x, cos 2x over cos squared x dx. Right, I think the question has said by expressing, so I think the first move that we would make here is kind of an obvious one. We would replace that cos 2x. Would we? Oh no, hang on, we need to do it the other way around, don't we? We need to think about how we're going to link these things together. Well, I think I am, yeah. The question did say, by expressing cos 2x in that form. Now it's slightly unusual for us, because we're really used to using this identity the other way around, and getting cos squared x written in terms of cos 2x. But we'll go with what the question has suggested, and we'll rewrite it. So that's 2 cos squared x minus 1 over cos squared x dx. I reckon that quite a few people with this question will have made life more difficult for themselves by going from here to saying cos squared x equals, and then replacing the cos squared x. And that makes it a much more difficult question to proceed with. We can uncommon denominatorise this fraction, can't we? It is a real word. Ooh. Because this is going to be 2 cos squared x over cos squared x minus 1 over cos squared x dx.
I know, that's the point.
And this first bit, the cos squared x, really nicely cancels out to leave us with 2. And can you see how nicely this has worked out? 1 over cos squared x is sec squared x, which is a good thing to have appearing in an integral. So we've now ended up with something quite nice to integrate. We get 2x minus 10x between pi over 3 and pi over 4. And this question, I haven't checked, but it will have said, it did say exact value, notice this. So don't kind of just go for a decimal answer out of this. Put the limits in, and we're going to get 2 pi over 3 minus tan of pi over 3, we'll put it all in first. Take away 2 pi over 4 minus tan of pi by 4, and we've got some math stuff going on now. We've got 2/3 of pi, take away a half pi, so that's a sixth of pi. Tan of pi over 3. What's tan of pi over 3? That's root 3. Does it see here, is he? Yeah. Yeah. So tan of 60 is root 3. Oh, just have it. What happened? I've got a new calculator. It is root 3. And then we've got minus tan of pi by 4, and tan of pi by 4 is... Oh, I've got the calculator. It's 1, isn't it? There we go. So that's plus 1. Is that right? And there's our answer. And I did say give it exact. There you go. Oh, yeah. That's all right. Are we okay? Oh, that's a nice answer there. Everybody happy?
Yep.